name is Jake Nelson. Today I'll be presenting my analysis of Felix Baumgart's record-breaking jump from the stratosphere known as the Human Rocket. Um, in this lab, Felix descended from approximately 39,000 meters above the Earth, and my goal was to use the energy principle to calculate his final velocity, determine the minimum altitude needed to break the sound barrier, and use a glow script model to see if our theoretical energy conservation holds up against a simulation. To start, we define our system as Felix, the Earth, and the air. By including all three, we treat the system as isolated, meaning there are no external surroundings doing work on it. This setup allows us to track the transformation of gravitational potential energy into kinetic energy as Felix attempts to break the sound barrier. So the core of this lab is the principle of conservation of energy. So as Felix falls, his potential energy should decrease in exact proportion to the increase in his kinetic energy. And our glow script model will test if this total energy remains constant throughout the motion. We start with Felix at rest at an altitude of 38,969 meters. So the physics here relies on Newton's second law, which is F equals ma, and the energy principle. We use the position and velocity update formulas to step through the motion. Mathematically, we define gravitational potential energy as U grav equals mgh and kinetic energy as k equals 1/2 mv squared. Because the Earth and air inside our system, work is zero. So here's the data we're working with. Felix's total weight with his suit was 118 kilograms. He jumped from 38,969.4 meters and deployed his parachute at 2,566.7 meters, resulting in a total free fall distance of 36,402.6 meters. His top speed during the actual jump was roughly 843 miles per hour. Using the energy principle, where initial potential energy equals final kinetic energy, we can solve for velocity, which is v equals the square root of 2 times g times h. And then plugging in our free fall distance, the theoretical final velocity at the moment he pulls his parachute is 845.1 meters per second. So what if the goal was simply to reach the speed of sound, which is 343 meters per second? So solving for h, we find he would only need a jump height of 5,996.4 meters. However, to allow enough room for a safe parachute deployment, using the 2,566 meter buffer from his real jump, he would actually need to jump from at least 8,563.1 meters. To simulate this, I used GlowScript. I initialized the ball, which represented Felix, with a mass of 118 kilograms and a starting height of 38,969.4 meters. I also set up the energy variables for kinetic, potential, and total energy to be plotted in real time. The simulation runs a loop for the 260 seconds of Felix's freefall, and in each step it calculates the net force from gravity, then it updates the position and velocity, and then it stops the simulation the moment the ball hits the ground. So looking at the results, our velocity graph shows a constant downward acceleration, reaching the calculated speed of 845.1 meters per second, and then most importantly, the energy graphs confirm the energy principle. The potential energy curve and kinetic energy curve are perfect inverses, and if we add them together, the total energy line would be perfectly flat. So there were some errors. Because the model is a simplification, the system is isolated, but in reality, air resistance would perform work on Felix, which would turn some of that kinetic energy into thermal energy. We also treated Felix as a point mass with no drag and assumed he fell in a perfectly straight line, which ignores the horizontal drift he likely experienced. So this brings us to terminal velocity. If we had included air resistance, Felix would eventually reach a point where the drag force equals the force of gravity, resulting in a net force of 0 and no further acceleration. To reach terminal velocity sooner, he would have to increase his surface area by spreading his limbs. And then finally, what if Felix jumped without his 31.75 kilogram suit? So interestingly enough, in a vacuum, which our current model is, the time of freefall would not change. As shown by the formula, T equals square root of 2h over g. Time depends only on height and gravity, not mass. So thank you for listening.